All right, so move on to box C here. This is equations of lines in space. And when we're talking about lines in space, all we really mean here is that we're now talking about 3 dimensions. These are 3D lines. Everything that we do here in 3 dimensions is completely analogous to what we did in 2 dimensions. So we're going to look at 3 forms for the equation we can have. First off is vector equation, which, as I said, is very similar to the vector equation in 2 dimensions. R here represents the direction vector from the origin to any given point on the line. We can express this as that vector as x, y, z. So again, the vector from the origin to any point that is going to be on our line. And this can be made up of some point that we know is on our line. We'll call it x naught, y naught, z naught. So this is some point on the line. Plus t times this. T again is our scalar, times a direction vector, which we'll just call ABC. This is our direction vector. So once again, very similar to our 2-dimensional equation, except, again, we've got this z coordinate in both our direction vector and in the coordinates for our points. Just like we did in 2 dimensions, we can take our vector equation and separate it out into our parametric equations. Instead of having 2 parametric equations, we're going to have 3 this time. So we take out our x component, we get x naught plus a times t. Our y's are going to be y naught plus b times t, and our z is going to be z naught plus c times t. So 3 parametric equations for this line. And the third equation that we're going to look at here is what's called the symmetric equations. And you always get the symmetric equations from the parametric equations. We can take each of our 3 parametric equations and rearrange them to solve for t. So if I bring the x naught over to the other side, I get x minus x naught, then divide through by the a, and that's going to be my expression for t. I can do the exact same thing for my y equation and my z equation. That'll give me t equals y minus y naught over b, and t equals z minus z naught over c. Because each of these expressions is t equals something, and the value of t has to be the same in each of these parametric equations to specify a particular point, we can take all of these and write them as being equal to each other. So we get x minus x naught divided by a is equal to y minus y naught divided by b, which is in turn equal to z minus z naught over c. And when we write it like this, these are called the symmetric equations for this line. Okay? So in just another way of writing the exact same thing that we saw before. The last thing to note is that there is no scalar or Cartesian equation in 3 dimensions for a line. And you can think of this because, like, imagine you have a line in 3 dimensions. The scalar equation is defined by the normal to this line. So you want a single vector that is perpendicular to this line that you're given. Well, in 3 dimensions, you have an infinite number of possible normals. I mean, if you got a line kind of like this is a possible normal. So is this, so is this, so is this. Like, any line sort of going around it is going to be a valid normal to that line. So you never have a unique, you could never have a unique scalar equation. So we don't talk about scalar equation. We will in the next unit, when we start talking about planes, we'll have scalar or Cartesian equations of planes in 3 dimensions. Okay?